Alrighty, guys, can you hear me? How are we all doing? Are there any questions before we get started? Any questions before we get started on the either homework or or the lectures? Okay, so we started last time on topology, so we're going to continue on topologies, right? So last time we talked about open sets, and we talked about them in RD. D is some natural number. So we say that a set A is open if so A here is a subset. A here is a subset of RD. A is a subset of RD, and it's open if you take a point in there. For any point inside the set, I can find a ball. So balls are given by epsilons. There exists a small radius such that the ball centered at the point is inside A. All right, so on a picture, if this here is your A, what you need to be able to do is to take anything that's inside here, so call that my X. You need to be able to find a little ball with radius epsilon that sits inside the set A. So that's what it means to be open. So the topology consists of the open sets. So when we talk about the topology, so the standard topology, this is V epsilon. We just write out explicitly what this V epsilon is. But this here is defined to be those points Y over in RD such that they are within epsilon of X. So we refer to these ones here as neighborhoods or open balls. These are the open balls. So the standard topology on RD is it's a set of all open sets. So that's what an open set is. Closed sets is the complement. So F is closed if the complement, right? So the complement of those Y's again inside RD, such that Y does not belong to F. So those are the closed sets. So lots of sets are closed, lots of sets are open, and lots of sets are not open and not closed. The thing we ended up talking about last time was the definition of limit points. So the limit points and these should not be confused, as I mentioned a few times last time, these should not be confused with limits of a sequence. Limit points for a set A. Again, the set A is always something in RD in our course. So X, again, a point in RD, may or may not be inside A. This is called a limit point. For the set. If you take, for any epsilon, it's true that the neighborhood, that the open ball centered at the point you remove the point X from it. Right, so I take the ball, I take the center away, and I intersect with A. I'm going to be not empty. If that's the case, I'm going to call this point for a limit point. So last time, some texts call these points for accumulation points. And it can be a bit confusing to look at this thing here. We looked at some examples last time. Maybe I should just go. I should just revisit them fairly quickly, right? We also have a definition of a cluster point, and that's different. So if I took what was it we had? We had a sequence of this one we have had so many times, -1 to the nth. So this is the one that jumps between being 1 and -1. There's no limit. It does not converge. It has two cluster points. It has two cluster points, so it will be -1 and 1. But these cluster points are not going to be limit points, because to be a limit point, I have to be able to remove them and then stay inside the neighborhood. And it has 0 limit points. If we also had that one last time. If you instead looked at AN, so same structure, but let's just scale it a little bit. Then this sequence here, it does not converge. But because this part here, this converges to 1, right? And this thing here, this oscillates. Oscillates, I think this is right, oscillates. It doesn't converge, and it has cluster and limit points. -1 and 1. So this sequence here never becomes equal to this one here, is always not inside -1 and 1. Whereas this one here is exactly the opposite. This is inside that set all the time. So limit points, they define according to this formula. You take any given neighborhood, any given open ball, you remove the center, and you demand that that resulting set intersects A. So this is what we had last time. We should Oh, so why is it called a limit point? Right, this is hidden in this lemma here. I want to prove that one. Right, so x, and let me just write it down in R. X in R is a limit point for a set. Okay, if and only if x is the limit of some sequence of a sequence an that's inside A. And we always have to remember this less than, so I need to make sure here that an cannot be x. So this is why this is where the name is coming from. We'll try to give a proof for this. So there are two directions, there's an up and a down. So first we take a point that satisfies the definition of being a limit point. And then we prove that such a sequence exists. So the down direction. So let x be a limit point. And then consider, we're going to look at the balls that have radius 1/n. The balls that have radius 1/n, right? So again, what's the definition? It means it's those points, and now we're playing in R, such that the distance between x and those points is less than the radius 1/n. Why 1/n? We could have chosen many other things. It doesn't have to be 1/n. We could have chosen many other things here. I need something that shrinks. So as n goes to infinity, 1/n goes to 0. That's the only property that I need. It doesn't have to be 1/n. It could be many other things. Last time we were playing with like 1/2 to the n, which goes to 0 much faster. Here, the speed that it converts to 0 is not relevant. But it doesn't have to be 1/n. You could have picked many other ones here. The only thing that's important is that these neighborhoods around x, they shrink as n goes to infinity. It doesn't have to be this one, but this one here will do it. So now we use the property of being a cluster point, right? When I take this one, b 1/n of x, I remove x from it. This one is not empty when I intersect with A. But this is not empty, so I can choose say pick. So this set here is not empty, so pick an in there. I can do that because the definition of being a limit point is that this intersection is not empty. Okay, so there's got to be something in there. And I pick one of the things that are in there. There could be many. But there is something in there, and I'll pick it and I'll call it an, right? And then we know, well, an is going to be close to x. I know that an and x are close to satisfy this. And so what remains is just to prove here that an indeed converges to x as n goes to plus infinity, right? But that's not difficult because of this bound here. So the only property I need when I choose this 1 over n, the only property I need is that this thing vanishes. I could have put many other things here. That will give me the convergence. The other way, this was the down direction. So we also have an up direction. We have convergence. So x is given as a limit point of a sequence that's inside A. So let x be equal to this limit. An is not x, and an belongs to A. Now we want to prove that on the limit point. So here I'm giving as a limit of a sequence. Now I want to prove that I satisfy the property up there. Okay, so what do we have? Well, if I'm the limit, right? So what does it mean to be a limit? It means that for any epsilon bigger than 0, if I get sufficiently far out in the tail, so when I'm bigger than some big number, then I know that an is going to be inside this v epsilon of x. And it's going to be in any ball around x. And this is, right, that's because I'm the limit. And clearly an is not equal to x, so it's also going to belong to this one. So there I have it, right? An belongs to this set, and it belongs to A, so it also belongs to this set. And then I'm good, because that's exactly what the definition says. So it's an equivalent characterization of what it means to be a limit point. It simply just says that if I take a set, then the limit points coming associated with that set, they can be realized through sequences. And so let's try to look at some examples. Do we have any questions about the proof? To get a feeling for these limit points, maybe we can consider, if I look at, I take A to be, say, 0 to 1. So what kind of limit points do I have? So the claim here is that this one here contains all its limit points. Right, because what I do is I take a sequence xn inside the interval 0 to 1, and let it converge. And consider where the limit can go. Where can, if I take sequences inside the interval, the closed interval 0 to 1, what can they converge to? You can converge to 0 and 1. They could also converge to a half, right? You could also converge to a half. Where can they go? Well, at least 0 and at most 1. That's correct, Fernando. at least 0. That's because if I have xn squeezed in between 0 and 1, then we had a result from weeks ago that said that, well, then the limit is going to obey the same bounds. Right, so they're always going to be there. You can only go you can only stay within this interval. What about if I looked at it, if I just changed it a little bit, if I said a should be, say, 0 to 1, and I'll keep it open here. Then, so what are the limit points? There's going to be all the points in here, but what else? Then also x equal to 1 is a limit point. Can I find a sequence that's inside this interval that will converge to 1? How could I choose my sequence? I need something that goes to 1. Very good. 1 minus 1 over n. This thing here converges to 1. Very good. Then we can do a little bit more complicated example, perhaps. So if I take a to be the rationals, take a to be the rationals. No, not the rationals. The rationals q, not r. Q. So what is the set of what is the set of A's limit points is what? Very good. This is R. And why is it true? Well, we had a property a while ago that said that Q is dense in R. Right. So if I take A and B in R, A less than B, then I can find a rational such that the rational is squeezed in between A and B. So that means that you're dense. So what are the set of limit points? Well, if I take a point in R, I want to prove that it's a limit point. Maybe we should call it X. Take X in R. Then we consider these balls V 1 over n. So again, I choose 1 over n. It doesn't have to be like that, but it's good enough to get the convergence. So now I'm looking at those points that will bring me close to X. So those Y's that will bring me close to X. Right. So what does this thing here mean? I am in R, right? So what it means is that X means that Y belongs to an interval X minus 1 over n to X plus 1 over n. And this is exactly the property I have up here. So I can find so we can find inside this set here, we can find points in here by this density argument, right? Between any two real numbers, I can find rational numbers. Right, so I can find a rational number that's in here. So this thing belongs to X minus 1 over n, X plus 1 over n. I can find it, and of course I can find it that it's going to be different different than x, and it's going to be in the rationals. And then I can do this for all n. So this sequence here satisfies that the distance between the point and x is less than 1 over n, right? And so we converge. So I can find a sequence of rational numbers that will approximate any real number, and we get the conclusion. So these are the things we talked about last time. There are maybe a few more examples in here, but overall, this is what we talked about last time. So again, I don't particularly care for this phrase, limit points. I think having called it something else, as I said, some texts call this for accumulation points. I wish the textbook and all the other texts that are using this language, they would have called it something else than limit points, because you can have as we talked about last time, you can have like the constant sequence does not have a limit point, and I find that a bit, the language is unfortunate, but hopefully these examples here make it clear. Any other questions before we move on? So we talked about a bunch of different concepts, and there are many more related to topology. So let me try to give you just a list of some of the concepts. There are other concepts. There's something called the interior. The interior of a set. The interior is denoted by A and then this circle up here. So what does it mean? So X belongs to the interior of a set A if I can find a ball around it. If I can find a ball around it, it exists an epsilon such that the ball radius epsilon, center X, is inside the set. So it could be empty. This could be empty. We'll see a few examples coming up when I'm done with all the concepts. So the interior, it is this A circle, and it's those points inside A. It's those points inside A that has this property. So it's a set inside A such that you're in that inside there. If you can put a little ball around, around the point and stay inside it, then you're in the interior. It could be empty. It's always open. A circle is always open. So we have the interior. We also have the closure. The closure. This is A bar. This is the smallest closed set containing A. So this time here, A bar is bigger, right? So A bar is bigger. Up here, it was inside the other one. Oh, that was a question. How is it different from just being an open set? Is that the first question? I mean, the interior, you have to be inside. You're the interior of a set. It has to be open, yes, but it also has to satisfy more properties. it is not enough just to be open, right? It's related to a set A. Right, so it's those points inside a set A for which you can find a ball around them, and that entire ball is going to be inside.
But I thought for like all points in A, you can find the ball.
No, you cannot. That's not possible. Yeah, so let's so maybe we should look at an example. So there's one more concept here. So leave a little space on your paper, right? So if you looked at A to be say, follow my own notes here. I take A to be 0. We take A to be 0, 1. Then if you consider, if you take a point like a half, then so x equal to a half, yes, that belongs into the interior. But if I take 1, I am not in there. Right, because I go out to 1, this point is included. And so what I need to do is I need to be able to put a ball around 1, right? So the ball is like that. And here you'll have epsilon, and here you have minus epsilon. But this interval here, this is nowhere, this is not inside A. So that's not in there. Whereas if we looked at, if I looked at the interval from 0 to 1, then if I looked at the interior, no matter which point I pick between the 0 and 1, I can always find a ball around it. So here A is equal to the interior. So the interior, the closure, and then the difference. Then the difference here you'll have this is called the boundary. So the boundary. The boundary of A. This is denoted by this. You might recognize this from partial derivatives. It's the same symbol. So the boundary of A, this is defined to be the closure less the interior. So interior, this is an open set. Closure, take a set that contains, so if you wanted to, this one here is not closed. So if I want to close A, what is the smallest closed set that contains A in this second example here? What would that be? Look there. This is right. This is the closed interval. Right, and so if you look at this, you have that the and what would be the boundary? Right, this would be the difference between the two. This would be 0, 1. I had another example. This is related to your next homework, so let's just walk through it. If I took A to be 1 over n is in the natural numbers. Right, so this is an infinite string of points. So it's like 1, a half, and a third, and so on. What would be would be the interior here. Mm, 0, 1. Well, not, I don't think so, right? So if this is true, then this would imply if I take x to be a half, this would imply that x equal to half would have a ball. So say the epsilon of a half, that would be inside A. Right, and remember what this one here is. This is those points in R such that the distance between those points and a half is going to be less than epsilon. Is that something inside A? But Andrew's right. This is not true. The correct one is that A has an empty interior. We cannot do this. This is way too punctured to do that. But we can look at the closure. What about the closure? So there are two guesses now. The closure, okay, so we have A itself. So we have three guesses now. We have 0, 1, open 0, 1, and we have A. Okay, so which one is it? Maybe there are other people who want to chime in. A itself. I want to leave room for you for one more. So there's one here. This is my guess. It's down there. Right. Why did we do these limit points? One way to describe the closure. One way to describe the closure is as a lemma. A's closure equals A union and then A's limit points. So to get the closure, so like to prove this, the textbook proves it. I didn't plan on proving that in class, but at least maybe have a look at it. So what does he say? Right, that's what he's writing down here. The closure of A is what you have here, A union all the limit points. He uses this as a definition, and then he moves on to saying that the closure is the smallest closed set containing A, which is my definition. These two things are the same. Actually, it's just a little proof here. So knowing that now, would we care to offer another one? So 1 over n, what kind of limits can I get out from 1 over n? That's right. So Fernando, you want to have A union 0. Very good. So not that one, not that one, not that. This one is good. So you can also see here that the boundary of A, remember what it was, this was A's closure minus its interior. And you want to end up here with A union that. So this was a bit about other things that often appear. So you talk about open set, talk about closed sets, and then you take an arbitrary set, and then you want to look at the closure of it. You're going to get a closed set. So you're looking at something that is bigger, but not too big, right? So it's the smallest big set that is closed. And the same thing with the interior, like this is you want a big set that is open, and you want the biggest possible, right? But it has to be inside. So this A open here, this is the biggest open set that's inside A, right? And then you look at the differences, and this is where you get the boundary points. So you take a set, you can do these operations on it. Yeah. Any questions on this? If not, then we want to move into a new concept, which is and one of these topological invariants. Right? So this set here, this structure we're going to move into. We're in chapter 3 right now. We're going to move into 3.3, the compact sets. So that is compact sets are. They are everywhere to be found. So we're going to talk about compactness now. This is section 3.3, compactness. So when I was reading through it, he kind of does it a little bit backwards. It's all fine what he does, but it's a little bit like what we looked at here. The way to define a closed set, it's to use this property that it's a set that contains the original set and is closed, and it's the smallest of sets with that property. That's the definition, right? And then you can give a characterization of it in the space that you're working in. In this case, it's an R. So here he does the same thing. He, instead of introducing the general concept that always works, he introduced the concept in this specific case that he's interested in. And then he proves that, yes, the two concepts are equivalent in this specific case. And the problem I'm having with that is that if, as soon as you move into something that is more complicated, then you won't have these properties. It will no longer be true. There have been some questions from you guys about, like, so what is this general stuff that I'm talking about? So here, this is one of my favorite books of all time. If you're ever interested in analysis that is like the general case, so this infinite dimensional analysis, and you can see this is a thick guy. Unfortunately, because when books are thick, they easily rip. So I have like loose pages in here. But this is like a 700-page Bible full of theorems. And what is nice about it is that it's the subtitle is A Hitchhiker's Guide. Right, so this book here, this will do these theorems that we're talking about in the general case. Right, and it's the surprising fact about this here is a math book, but it's actually written by economists. So, and when you flip through it, it's theorem after theorem after theorem. This is an awesome book. And of course, inside here, there's a discussion of compactness. There's a discussion of compactness. You will find it somewhere. You can see there are lots of words with compactness, right? And you use the general structure. So this, if you have such interest, if you're interested in like a text that will take you and show you what the general full picture is, something like this textbook, this is absolutely to be recommended. It's a modern text. It's a big thick, and it's also something you don't just read, of course. But yeah, that would be my recommendation. I bought it many years ago, and this is a third edition. It's been out in a number of editions. Unfortunately, one of the authors passed away a few years ago, so I don't know if there'll be a modern one, but it's expensive. So what I would like to do instead is, then instead of introducing these general concepts in this specific case that we're studying, I would rather have the general concept come in first. Right? So the general definition is, we're going to be talking about this. The general definition uses what's called open covers. And these things are discussed in our text. It just comes much later. It just uses open covers. And so what is an open cover? But it's an open set. Okay, so here we say that K inside RD, say, is compact if any open cover. So what is an open cover? So this is one I want to write here in parentheses, IIE. This is a collection. It's called an O, and then we index them by lambda, as we've done before. So any set, any collection, any set of open sets. This is any collection or any set of open sets covering K. That means you take a union. Take a union of all these open covers, and it's big. It covers K. Can be thinned. Can be thinned to a, and here comes the critical word, finite, right? So you take any and you go to finite. So a finite cover. So you have O lambda n, and then n would go from 1 to capital N. This would be a subcover, so this has to be inside the bigger one, O lambda. So you can extract finitely many of these open sets, and you still cover. So when I take the union, of these finitely many, I still cover K. No, parentheses are way off here. I take an open cover, can be thinned to a finite cover. And now there are too many parentheses. Too many parentheses. So you can thin out. You take a collection of open sets, any collection you want. You take the union of them, you cover the set. Such a collection can be thinned out to a finite cover. And that finite cover, when you take the union, still includes K. So Abbott he does not like to do this level of abstraction. He doesn't like to do this. He uses a much simpler definition. He says K inside RD is compact if K is bounded and closed. So that surely seems to be a lot easier to digest than all this mess up here with covers. This is probably why he does it. So Abbott, he uses this one. I am claiming that it is this abstract nonsense up here that is the much better definition because it works in all kinds of settings. Okay, and then of course you have to prove that all these things are the same. So let me write down the big result here. And this is what we're going to be proving. This is going to be what we'll be proving next time. So the big result is this Heine-Borel. This is the Heine-Borel theorem. Right, so this is the one. It says you take a set in RD. Then K is compact. K is compact. This here is in our sense, or yeah, depending on, so K is compact, and this is the same as saying that K is closed and bounded. And this is the same as saying that K is sequentially, what's called sequentially compact, so I need to define that too. K is sequentially compact. So what does that mean? You take any sequence xn inside K. Any sequence inside K has a convergent subsequence. So it's called xn m. So it's a subsequence. It's a convergent subsequence xn m, which converges inside K. Right, so the limit of that subsequence is inside K. So this is the big result. So if you take this abstract definition up here, you can prove that this abstract definition is equivalent to K being closed and bound, is equivalent to it's sequentially compact. So it means that you take a sequence inside the set, that sequence is going to have a convergent subsequence that has a limit inside the set K. These things are all the same. And this here is this result. This result is false in general. If you move away from RD, this won't work. I had prepared a little example about that, but let's do a few examples about where it does work, and then let me show you, at least give you an idea about why you should not expect something like this here to work. Right? There's a reason why this Bible here, the Hitchhiker's Guide, is called infinite dimensional analysis. Right? Infinite dimensional analysis, and the reason that this is finite dimensional, right? This D here a finite number, right? So this is a simpler case compared to the general one. And so when you have a simpler case, you have more structure. And this is false in general for, say, the space Rn that we have looked at already, right? Just the space of real sequences. Okay, so let's do a few examples, and then next time I'll prove the Heine-Borel theorem. Let's look at some examples and see if we can get a feeling for what a compact set is. We start out by taking the set 0 to 1, and then leave it open here, right? This is not compact. This is not compact, right? Because it's not closed. So if I close it, this is compact. This is a closed bounded interval. That one works. Maybe we should have a word about these subcovers in this case here, right? We're talking about these in the Heine-Borel theorem, right? We're talking about subcovers up here, the definition of what it means to be compact. So maybe we should revisit these two things here in let's have a look at these using subcovers. Let's try to understand these statements here using subcovers. And how would that be? Well, if you go about maybe taking a set like, if I take a set like 0 to 1, so this is not compact. So if it's not compact, then it means that there is a cover. Yeah, so Priya, this is spot on. This is what I'm trying to do here about the open cover. So this is not compact. Okay, so that means that there should be like a cover that can't be thinned. Okay, so let's try to look at a specific cover. So if I take lambda, like I'm indexing my covers. I'm indexing my covers here by lambda. So I'm going to continue to do that. I'll index them by lambda. So I take a lambda into 0, 1. Take a lambda into 0 to 1, and then consider the open set to be something like lambda divided by 2 to 1. These are open sets that cover this interval 0 to 1, right? Because if I take the union over all such lambdas is running between 0 and 1. If I take the union here of these O lambdas, what do I get? What do I get? Well, top part here is a 1. What is the bottom part? Well, lambda runs all the way down to 0, right? It does not become equal to 0. It runs all the way down to 0. So this is a 0, and then I have open here. Right, so this is this is an open cover. These guys here, they form an open cover of the interval 0 to 1. And can we thin it? So can we thin it? Can we thin O lambda to say O lambda n? Can we thin it such that, well, we need the same property, but for the thinned out one? Can we do that? Well, let's try it out. What are we going to get here? We'll take the union. This is going to be the union into n, and then what we have here would be lambda n divided by 2 to 1. Can we thin it such that inside here you'll find the interval 0 to 1? Is that possible? Well, what is this union over here equal to? Priya, you sure you want to say largest? Smallest, okay, I agree. So you want to do the min here? But that's not the case, right? You don't have this inclusion. Right, so this is not true. So we were able to give, we were able to create an open cover that you can't thin it. Well, if you can't thin it, then the set is not compact. If you want to be able to have a compact set, you need to be able to thin all and every single open cover to a finite cover. The answer is no. Does that make sense to you guys? Let's try to turn the situation around a little bit and maybe look at, go back and maybe take this one here. This is closed and bounded. Okay, so Priya, so you want the union of the infinite cover to be a subset of the finite open cover. No, I don't want that. I want the original set. The original set that I'm interested in here, 0 to 1. I am not saying anything about these unions between the finite and the infinite covers to be the same. I'm not making any such. This one here is obviously always going to be bigger than any smaller one, but I'm not saying that these two really have to be the same. The only property that these two here should satisfy is that you both contain K, the set in question. And that's the general property. Right? So you take a cover, what does it mean? I take the union and then I contain the set. Now, what does it mean to thin it out to a finite subcover? Well, it means that I still have the covering property, right? So the union of that finite stuff, the finite union of these open sets, they must still contain K. But I'm not saying anything about how that union should relate to this union here. Yeah, no other questions? Well, let's spend the last few minutes maybe talking about the example where we have compactness. So if we return to the the example that is closed and bounded. So this one. Now, apparently, any open cover that you can cook up can be thinned out to a finite one. Okay, so let's look at a specific example and see how to thin it. So let's create an open cover. Right, so we have so from before we had the O lambdas. These were these guys, right, for lambda running between 0 and 1. But we need to worry about the endpoints here. So we're going to be looking at the cover. So we consider the cover. I need to have an open set that will encapsulate 0. So let me do -1/2 to 1/2, say. Then I also need something up on the other end. This could be 1/2 to maybe 3/2. And then all these old lambdas. When I take the union of all these, when I take the union here of O in this mess here, I am definitely going to get something that is bigger than the interval 0 to 1. Okay, so because it's compact, I need to be able to think. Because this is compact, and here I'm using that it's bounded and closed. The reason it is bounded and closed, we can thin. We can thin the cover to a finite. Which one should we use? Come up with an easy one. First two. Okay, we do the first two. And 1/2. I'm not sure I understand with the 1/2. What does that mean? I cannot just, I can only use sets that are up here, right? This is what it means to be a subcover, right? I can only use sets that are in here. I need to thin out the cover to a finite one. Right? So I cannot put a 1/2 here. This is not going to work. So what can I put? Yes, I can put that. This is a finite cover, right? And this one here is inside. It's inside the bigger one. So this doesn't prove that it's compact, right? This is something that has to be true. Otherwise, there's a problem with the Heine-Borel theorem. The first argument shows that we cannot have compactness because we found a subcover that we couldn't thin. Here we're just illustrating that we can thin out a specific cover to a finite one. Are there any questions about what we've been doing here? We have like a few minutes left, so let me just maybe try to hint at when you move into these more general spaces. why wouldn't it work if we have 0, 1? I'm not sure I understand. What do you mean? Why wouldn't it work if we have 0, 1? Why would not what work? Yeah, this one here is not compact, right? So we took an abstract, we took this interval, and then we said, okay, here's an open cover. Now let's try to thin that. Let's try to thin that open cover and see if we could do it. So Priya said that the problem is that you run down to here, and this interval here, min of lambda n over these n's between 1 and capital N, this min here, this cannot be 0. That's the problem, right? So the min from 1 up to capital N of lambda n, this is going to be strictly positive. Does that make sense?
Yeah, but what if we like go with the way that we did the last example, right? If we like add this additional intervals that will cover 0, it still not work?
What would happen if we? Oh, be careful now. So be careful, right? Because if I take the one from the previous one, then you'll be able to thin that cover. That doesn't prove that that you're not compact. Right? You're guaranteed that you can be able to thin when you're compact. Right. So so the implications are going the wrong way. Right? This one here, how do I prove that this is not compact? Well, I prove that this is not compact by constructing one cover that you cannot thin. I cannot just because I can find one subcover that I can thin, that doesn't show that I'm not compact.
I see. Okay.
Yep. So there are to be compact, you need to be able to thin all subcovers. All covers to find out subcovers.
Okay, I got it. Thanks.
Okay, any other questions? So the last few minutes, let me just try to hint at what could potentially go wrong if you moved into infinite dimensions. This is a statement down here. Like, look at a statement like this one. If you're sequentially compact, and this is equivalent to all these properties up here, like, then that means you take any sequence has a convergent subsequence, and you can quite easily get into trouble here, because if you look at if I look at what could it be? If I looked at say the interval 0 to 1 to the nth. So if I take an x in here, then x is a humongous long vector. But this is x1, x2, so on, xn, and it keeps going. So what I could do is I could create I need a bounded so can we create a bounded sequence? With no convergent subsequence. Well, yeah, you can say you can say that I want to have, I don't know what to call it, maybe call it for A1. This is going to be, there's going to be 1 here and then zeros everywhere else. I'm going to create A2. This is going to be 0, 1, 0, 0 everywhere else, and so on. And AN going to be 0, 0, 0, and then there'll be 1 here in the end spot, and so on. And you keep doing this. So these are the bases. This is the basis elements. I keep bounded. You bounded in length by 1. But you don't have, there's no convergent subsequence. There's no way, if I look at A in K, I call it M here, there's just no way that this thing can converge. And the problem is that this 1 here keeps getting pushed out. As you move out in the sequence, this 1 just keeps getting pushed down further and further and further, and there's nowhere for it to converge inside the space. So this is and this shows so bounded, and like this is a close bounded set, and then these are not compact in general. It takes a lot more to be bounded, to be compact in these infinite dimensional spaces. And if you're interested, try to Google. We've talked about Hilbert before. Try to Google Hilbert's cube. CUBE. Try to Google Hilbert's cube. This is an example of a compact set in an infinite dimensional space. It's going to be close and bounded, but it's going to be a lot more. If you're interested in such things, Hilbert's cube is a good place to start, and you can get a sense of why. I mean, here you're getting a sense of why there's something with the dimension. Is 1 here gets pushed away, and the setting that we are in, it's impossible to push it away because the dimension is fixed. Okay. I think we are out of time. Are there any more questions before we call it quits? I've asked your TA to get the homeworks graded over the weekend, and I'm hoping that Rebecca is going to be done with them soon. Are there any other questions before we say goodbye? And
Professor, could you please explain the difference between converges to infinity and diverges?
yeah, I can. But this is really just this is a question of taste. Right. So, so some authors say that this one here, this is our main example, right? Some authors say that this diverges to plus infinity. So I don't do that. So for me, this is not, that's not the problem. So to me, it converges to infinity, because what does it mean? You take any, for any big number, I can find somewhere some n such that whenever I'm later than that n, this number here is big. So maybe I should not call it trigonometric indices. So we call this k. of n, such that this is bigger than that big constant k. So let me not call it k, we call it m. So I will not say that. If to me, -1 to the nth diverges, stuff like this, sine n, stuff like this, they diverge. They don't have limits in R, and they do not converge to plus or minus infinity either. This is because you don't converge in R, and they don't converge to plus minus infinity either.
I remember you saying like if it grows fast enough, then it diverges. Or am I remembering?
This is for Cauchy sequences. So if for a Cauchy sequence, you need to be able to make xm minus xn. You need to be able to make this thing small. It needs to be small. So if only xn plus 1 minus xn is small, so only the next one out is small, you can have that xn diverges. So you need to have this property if you want to be Cauchy. And what we were talking about was that if only this one here is small, you can have the divergence. And so we looked at, but if it's really small, like something like this is like 1/2 to the nth. But then we show that xn actually converges. Then xn converges.
I guess what is like, is there a threshold between like what is this 1/2n? Like what is the threshold after which it converges?
There is not such
Or
there is not such a, it's not that simple.
so okay, so
Not that simple. We only have sufficient conditions here. You're saying that if something like this holds, then it converges. We were not proving any sort of necessity here.
okay.
But what we have up here is that if this is less than 1/n, this is not enough to get you convergence to a finite number. That's not enough. This is too slow in general. Then you could say, well, what about n?
Yeah.
What about n to the 100?
Yeah, exactly. Then what about them?
Yeah, what about them? I don't know. I don't know. I don't think this is fast enough. I think these are too slow.
So is after 1/2 to the end, that's fast enough, but before 1/2 to the end is not fast enough, or like we shouldn't worry ourselves with that?
I mean, can I find something that grows slower than 2 to the nth for which this thing still holds? I think I can. But I'm not. I think this stuff here, this is too slow. I think there's not going to be some miraculous function where you'll say that this here is equal to f of less than f of n, and f of n has some formula, f of x is equal to something, and then it works. You will not have that. There's no way you will find such a simple structure for something that is this complicated.
Okay.
There's no way. I have never seen it like this. And typically you end up in these, the unfortunate situation that you almost always end up in is this ambiguities. And we talked a little bit about this. We talked a little bit about it. We talked a little bit about you prove something with a ratio test. Where was that ratio test we did? Ratios at 78. Yes, right. So you have this thing here, and you can see that there's something with a 1. And then what you'll end up often in is that there's this critical threshold. And then lower than the threshold, you know what happens. And strictly bigger than the threshold, you know what happens. So typically you get convergence when it's smaller than, and then you get divergence when it's bigger than. But then there are all the cases where it's exactly equal to 1. And there it's just ambiguous. You don't know. And there's something called Weierstrass test. I don't know, maybe this is coming later. Yeah, see this over here, this Weierstrass M test. Let's see if he has an example about it there. No, he doesn't have it over here either. Yeah, so that there are some attempts to put some more structure on these X's and then try to find sharp like estimates over here. But you always end up with this critical value, like what we saw here with R being 1. If you're less than 1, you're good. If you're bigger than 1, it fails, but then you're exactly at 1. And the unfortunate thing is that almost all the interesting cases, they fall exactly at that critical threshold. And so, so you're kind of stuck.
Yeah.
You're kind of stuck then. But of course, the examples we give out in class, right, they're nice, they fall into one of the two clear domains, but in practice, this is just very rarely how it goes. It always ends up on this critical ambiguous case, and then it doesn't really, it's not so useful.
I guess if I have a couple more minutes, I can ask you one more question because it's related to the homework. Do you remember my homework example? If n is sine of n over n, and if n is prime, that n is equals to a of n equals to n.
Yes.
Would that be the one that converges to infinity or diverges?
So if you take xn to be n, then I would say that this converges to infinity. But you're welcome to say it diverges to infinity. This is fine.
But if you will put like that it equals n squared, would that be like strictly diverges? Or
no, this still converges to infinity.
Can you
I have a
make
question.
it diverge? Go ahead, Alex.
Okay. So like with this, right, if we can just like arbitrarily say that like, oh, like it either like converges or diverges at infinity, doesn't that sort of really change your response for like number 5 on the homework?
No. It does not. It doesn't, unless I made a mistake. Hang on, let me just.
Well, because if you say that a subsequence that like goes off to infinity, if you say that that converges,
read the full question. You need to read the full question.
Okay.
It says it converges to the same limit a in R. It doesn't say that it converges. It says that it converges to the same limit A in R, right? And infinity is not inside R.
Oh, I see. Okay. Yeah. Okay. Thank you.
Okay.
Yeah. Okay. Thanks. Sorry, Professor, for keeping you so long.
Please don't apologize. I mean, uh, in case you wondered, I really like math, and when there's some students that are interested in it, I'm just very happy. So don't apologize.
Okay. Okay.
Alrighty, guys.
All right. Have a good day. Bye-bye.
You too. Bye.
Thank you very much. Bye.
You're welcome.